Financial modeling, topic 2, estimating asset risk. In other words, volatility and standard deviations. In this topic, if you're looking for references, I recommend Simon Benenga's Financial Modeling, 4th edition. Chapter 8 covers portfolio models where you compute return mean, variance, standard deviation. Chapter 17 covers Black-Scholes and particularly calculating volatility using Black-Scholes implied volatility model. And you're looking for a web reference on EWMA, exponentially weighted moving average volatility, which is not covered in the textbook. I recommend this link here from Investopedia. So in this lecture, we're going to talk about, again, estimating asset risk or standard deviation. These are needed numbers that are needed to construct optimal portfolios, which we're going to do in the next topics. Plan for retirement or value stocks. In this lecture, in particular, we're going to understand the normal distribution. That's going to be section 1. We're going to compute asset return variance and standard deviation using formulas and functions. We're going to scale standard deviations across time. So how do I go from weekly to monthly to annual standard deviations? We're going to graph and compute the moving average volatility. We're going to compute exponentially weighted moving average volatility. And we're going to compute Black-Scholes implied volatility. So let's talk about distributions in nature. In our top panel, you see a graph of women's heights for a particular distribution or sampling of females. You have a mean about here, looks like it's about 65 inches. And you have men, looks like the average is about 70 some inches. And what you see is there's certain dispersion around the mean. So this is a histogram. So it's talking to me the frequency, this is the number of women at this height, and the number of men at this height, and so on. So what you see, there's a certain distribution around the mean for both women and men. Here's SAT scores. We have a mean at about this point here, and there's a certain distribution around the mean. We have birth weight in kilograms of a sample of babies, and what you see is you have a mean at about, about 3.5 kilograms, or what is that, about 7 or 8 pounds, and you have a certain distribution around that. And lastly, I dug this one up myself. Annual snowfall in Philadelphia is an average of about 25 inches. And what you have is a certain distribution. And actually what you see is you got some really big years. So in nature, there appears to be a normal distribution. And I'll put that quote unquote normal distribution around many items where there's a clustering in the middle, right? There's a central tendency. All right, and there seems to be some symmetry around the mean. Now here's a collection of randomly selected stocks, and what you see also, there seems to be central tendencies around expected return or historical returns, and a certain distribution around those returns. Again, there seems to be some kind of normal distribution of events. Now asset returns have shown this what we call bell-shaped curve, or I guess I can just say the bell-shaped curve, also called the Gaussian distribution. Now look at these two returns. Let's say that this green asset has a mean at about this level of return, let's call it 8. And this asset has a mean return of this, let's call that 4% return. And what you see is this green asset has a more dispersed distribution, so it's less risky. And what you see is this red asset, even though it's a lower expected return, has less risk, it's less dispersed. So if we describe these using a normal distribution, we'd have a mean, and then we'd have a measure of this dispersion. And so the question is, which asset is better? Well, clearly this green asset has a higher expected return, but also has a higher risk. We could wind up in these tails. Although I love these tails, I don't like this tail right here where you have very low returns. So it's not clear which one's better. What you see is it has a higher expected return in green and a higher risk. Now for assets, if you assume that asset returns are normally distributed as a computational shortcut, then you can fully describe the distribution of returns. So if you simply know the mean and standard deviation, and we make an assumption of normality, a Bell or a Gaussian distribution, then we can make all kinds of predictions about the likelihood of any event. So let's talk about some specific statistics. First of all, standard deviation. If I look at this bell-shaped curve right here that I just drew, if I look at this, I know we have a mean here, and we have some kind of measure of fatness of the bell curve. Right? If I go back to this data here, right, I need a measure of the fatness of this bell-shaped curve. So what we're going to do is to measure that bell-shaped the fatness of the bell-shaped curve. We're going to use a number called the standard deviation of the normal distribution. And it's a measure of dispersion, how spread out this data is, or are. So how we calculate the standard deviation? Well, we're going to say it's going to be the square root of the variance. We're going to write standard deviation as the Greek letter sigma. We're going to write variance as a sigma squared. So standard deviation is the square root of the variance. Now variance is what I've written here under the square root symbol here. The variance is going to be the average squared deviation from the mean. So in particular, if you have returns for say 40 months, I'm going to take the return in each month, we'll call it RT, minus the average of those 40 months and divide by 40. And I'm going to take the average square deviation from the mean is the measure of the dispersion around the mean. And to get rid of that squared term, I'll take the square root to get back to the original units, and that's why we call it standard deviation. Now, the mathematics of the normal curve were developed in about the 18th century and allows us to make statistical inference into the likelihood of events. So, for example, if you assume normality and we use the standard normal curve, we'll say we have a mean of 0. We can say things like, so if we know the mean and we've estimated the standard deviation, we can look at say between plus or minus 1 standard deviation. So we can make an inference that 68.26% of the outcomes, the expected dispersion, are going to be plus or minus 1 standard deviation of a mean. In other words, if I look at the area under this bell-shaped curve between plus or minus 1 standard deviation, that area is going to be 0.68. The sum of the entire area is 1 under the entire curve. So I can make an assumption that 68.26% of the time I'm plus or minus 1 standard deviation. If I look at plus or minus 2 standard deviations, I would have the area here. And that would be 95%, 95.4% of the time. And if I look plus or minus 3 standard deviations, that would be 99.74%. So think about the usefulness. If I can assume that asset returns, say the returns of the S&P 500 are normally distributed, and I estimate the mean and I estimate the standard deviation, I can estimate the probability or confidence interval for any level of return. Now, when we talk about the number of standard deviations away from the mean, we'll generally call that the Z variable, the number of standard deviations away from the mean. So let's make an assumption about the S&P 500. Let's say that the S&P 500, its expected return is normally distributed with a mean of 7 and a standard deviation of 16. If we make that assumption, we can use the mathematics of this curve to say that 68% of the time it's going to be between the mean and plus or minus 16%. So 68% of the time, the market in a given year, I'm 68% confident that returns are between minus 9 and plus 23. That's 7 minus 16 and 7 plus 16. I'm 95% confident it's plus or minus 2 standard deviations. In other words, plus or minus 32%. So I'm 95% confident this year that the returns of the S&P 500 will be between negative 25 and plus 39. And I'm 99.74% confident plus or minus 3 standard deviations. So between negative 41% and 55%. Now, in Excel, we could use a formula to calculate those probabilities. So, for example, if I use this, if you double-click on this spreadsheet or this PowerPoint, there's a spreadsheet built into it, and I typed in this formula. 2 times norm S dist, and I put in the number 3, minus 1, and it gives me 99.73%. So what that's telling me, the Z is the number of standard deviations away from the mean. So the area between plus 3 and minus 3 is 99.7%. And also I have this formula down here. If I put minus norm S inverse of 1 minus x over 2, where x is that probability of 99.73%, I could say that the z's, the number of standard deviations from the mean that correspond to a 99.73% confidence interval, is 3. Also, another use of these formulas, if I just use the norm s dist function and the norm s inverse function, what they're giving me are one-tailed tests. So for example, if I type in 1.645 standard deviations away from the mean, say positive 1.645 standard deviations away from the mean, the norm s dist point of 1.645 will give me a value of 95%. Now this is a one-tailed statistic, and what it's telling me that I'm 95% confident that the returns will be less than 1.645 above the mean. So this area here is 95%. This area is 5%. Now it works both ways. Since the normal distribution is a symmetric distribution, it is also telling me that if I'm minus 1.645 standard deviations, this area, including this, is also 95%. So that would tell me that I'm 95% confident that I will not have returns worse than 1.65 standard deviations lower than the mean. Now you can also use the norm s inverse function to do the other way around. I can get the 95% confidence interval for that one-tailed test. In other words, plug in the 95%, and it'll tell me that's associated with that critical z of 1.645. Now, if I double-click on the spreadsheet, what you can do is you can plug in 99% here and see what that critical z value is. Or I can plug in 2 here and see what the associated area is. Now, I just want to give you a cautionary note here, a little danger sign, like you see a road hazard, danger sign associated with this normal distribution. Many people simply assume distributions are normal to make statistical inference and to boil down this very complex concept of risk into a single number called standard deviation. But a big warning, not all distributions are normal and may cause errors in prediction. So let's take a little sampling I did here, hypothetical sampling. Okay, hypothetical sampling. I didn't actually sample this myself. However, if I took a room of 150 adults, men and women, and I gather statistics on one characteristic of them, and I did a distribution. What I found is that 75 people had 0 of that attribute, and 75% of those people, or 75 out of 150 of those people, had 2 of those attributes. So half the population has none, half the population have 2. This is not a normal distribution. There is no central tendency here, right? There's no bell-shaped curve. However, if I just assume it's a normal distribution and I calculate the mean, well, the mean, if half the people have 0 and half the people have 2, the mean will be 1. I will get a mean equal to 1. And if I calculate the standard deviation of that data set, where there are just a bunch of 0s and 2s, the standard deviation will be 1. Therefore, I would make predictions that the average person would have 1 of these attributes. And say, if I look at the, if I use this graph, right, I can say that, well, 0.13% of the people will have 3 over the mean, 3 times the mean. So 0.13% will have 4 of this attribute. Now let me tell you what that attribute is. This attribute is the number of testicles per human. These are the women that have none. These are the men that have 2. However, if I just assume normality, took the data set, calculated statistics, my prediction is that everyone, the typical person, has 1 with a nice dispersion around 1. A lot of people have 1.5, some people have a half, and so on. So be careful using normal distributions. So in this topic, we've talked about, or we've tried to understand what normal distributions mean. Right? Normal distributions is an assumption that the distributions of a particular observation will have a central tendency with the symmetric bell-shaped curve around it. Next topic, we'll talk about computing return variance and standard deviation using formulas and functions.